this, then what next? You have your current as 10 ampere. You can easily now fix this into our formula. And now our formula is what? Rs, which is the result of the shunt, equals to Ig Rg over I minus Ig. Sorry for the disconnection, everyone. Very sorry. So we have equals to what our Ig? 0.01 times what's our Rg? Our Rg becomes what? 2 ohms. And we're dividing it by I minus Ig, which is this our I here, 10 minus Ig, which is 0.01. And when we do this, we'll be having 0.02 divided by. Subtracting this gives us, when we subtract that, it gives us a value of 9.99. So 0.02 divided by 9.99 is going to give us what? Rs equals to a value of 2.0 and 2.002 times 10 raised to the power of minus 3 ohms. Then she wrote it just perfect as you're supposed to write it. This connected in parallel. If you don't write this connected in parallel, I dare you have just lost some marks. Desire, you're asking me to explain the formula. I already did that. You joined it. Now, what you do, Desire, this is so that you don't push the class backward. This is what you do. This is the formula actually. So I'm going to save the lecture and send it to the group. So you can easily click on the link and watch the beginning. You will see how we derived the stuff. You see how we derived it because of time. Now let's write this down. Let's write this one down. Let's write this one down. I believe you've written it down. So that's one thing. From next week, I already told you guys, I'm not going to be telling you connect. I'm not going to be telling you come online from 10 o'clock every day. Just do that our lecture. That's it. So you have to just be online. As I said, make preparation for data, sufficient data. You can get yourself 1.5 for 6 gigs, 1 week. You understand? Then you can be using 25 data to cross it over in case it wants to expire, so that it doesn't expire and waste and crossing it over. You get? Okay. Now to go to the next one. Now, really, the principle, what was the principle we used in this galvanometer to ammeter? We made it of the fact that in parallel connection, what is constant? Voltage. We now said voltage in the galvanometer was equals to the voltage in the what? In the shunt. Then we now explored that formula to give us authenticity to what we were solving. Okay, now, can I wipe this off? Can I rub off the board? Can I rub off the board so that we can go to the next concept? Let's be quick, let's be quick. My leg. Please, are we done? Can I rub it off? I want to rub it off. Oh. Okay, I'm opening it up now. So we're going to the next concept. Okay, Shubhami are done. So I'm going to the next concept, which is conversion of galvanometer to voltmeter. This is what we just did now. If you look at the question, we're talking about the galvanometer and the ammeter. But in the one we are going to want to look at how we can convert a galvanometer into a what? Into a voltmeter. And it's very simple. You have to, one thing is, it's not just about learning the calculation, it's also about learning the what? The concept, how to convert it. Because they can ask you in theory, demonstrate the conversion of the galvanometer to ammeter. You understand? So let's explore the conversion of a galvanometer now to a voltmeter. Conversion of galvanometer to voltmeter. Now, when we're converting from galvanometer to ammeter, we actually make use of a shunt. But when we're now converting from a galvanometer to a voltmeter, we're going to be making use of a multiplier. Are you getting me now? So we make use of a multiplier right now. So we actually connect the multiplier to the galvanometer in series. Remember, when we're dealing with converting to ammeter, we're connecting it in parallel. But right now, we're going to be connecting it in series to a high resistance called a multiplier. We're connecting the galvanometer in series with a high resistance called a multiplier. I see the differences between the ammeter converted to ammeter and voltmeter now. In ammeter, we're making use of a low resistance called a shunt connected in parallel to the galvanometer. But right now, in converting the galvanometer to voltmeter, we're connecting the multiplier, or a high resistance called multiplier in series with the galvanometer. So let's have that written down. To convert, or let me just go straight to the point. This is done by connecting the high resistance called a multiplier in series. Of course, in a series connection, what is constant? Current is constant in a series connection from our last class, but voltage is different. So the total voltage will be the sum of each volt. That means sum of the voltage in the galvanometer, the sum of the voltage in the multiplier. You get it now, that will give us the total volt. But the current in the multiplier and the current in the galvanometer will be equal. You understand? They'll be the same because it's constant series connection. So we said this is done by connecting a high resistance called a multiplier in series to the galvanometer. So to demonstrate that now, so we'll be doing something like this now. Let this be the multiplier now. Multiplier. Of course, they kind of understand. Then connecting it in series with with your galvanometer. Are you getting me now? You connected it in series with your galvanometer now. So I just want to do a demarcation here to explain something. Of course, if we're using this line like this as a potentiometer measurement for voltage, it means that from here, that is from this place here, to this place will be V, as the total voltage in the unit of this circuit. But you are going to be that from here to here will be the voltage in the multiplier. So this will be the voltage in the multiplier. While from here to here will be the voltage in the galvanometer. I get it now. So you are having voltage in multiplier, voltage in galvanometer. So if a current passes through it, the current passes through them, we are saying now current passes through. I get it now. The current that will pass through this multiplier, and this multiplier will be the same current that will pass through it, that will pass through this, pass through the galvanometer. I get it now. So we call that current I. So we don't need to call it IM and IG since the current are the same. I. Yes. So what can we say about V? Looking at this, we know that V, which is the total voltage, C equals to Vm plus Vg. Vm plus what? Vg. Are we together? Any problem? So Vm plus Vg. Now, express it, we know that we call V is equal to IR. So we can express it here. You don't understand desire. Let me repeat. This is what I'm saying. In your conversion from galvanometer to voltmeter, you connect a high resistor in series to the galvanometer. And that's what we're demonstrating here. This is the symbol for galvanometer. This is your multiplier. You are connecting it in series. Except you did not recall or read what we did in our last class. Okay. I thought you had a problem. All right. So, for those that just joined in, so we connected the series, and now we are saying that since the voltage that flows in the multiplier, this one is the volts that Vg is the one that flows in the galvanometer. The total volts in this will be Vm plus Vg, and recall that V is equals to IR. I get it now. Since V is equals to IR, you can now exploit it. I'll be saying V is equals to that the total voltage is equals to, and this voltage is the voltage that the galvanometer wants to measure. I get that but not going to change it. V equals to Vm now is what? I times what? Rm. That's the resistance of the multiplier. Rm. This one has the resistance of Rg. You get resistance of galvanometer with multiplier. Rm. You know I'm not writing Im because the current flowing through I and multiplier and galvanometer are the same. So there's no need of specifying Im and all this one. So the VRV plus what? What will be our VG? Our VG will be IRG. Remember that what we are emphasizing on is this special device called the multiplier. So we want to make Rm subject of formula. And since we are making Rm the subject of formula, we carry this to the other side, and that gives us IRM equals to V minus IRG. You see that now? IRM is equals to V minus IRG. Okay, then we divide both sides by I. Since we are looking for the resistance, the magnitude of the resistance that must be connected in what? In series with that galvanometer. That's why we're making RM. So remember when we're doing parameter, we're making RS instead of that. We want to know the resistance that must be connected in parallel when we're doing ammeter. But now resistance that will be connected in series. So that's the multiplier resistance. You get. They are divided both by I. So here I will cancel I value Rm equals to V minus IRG over I. So this is the formula for calculating the what? For calculating the resistors, for calculating the resistance that must be connected in series. You understand? I can see somebody saying it's actually very simple. Yeah, it's very, very simple. Very simple. No stress. So this is the formula. Let's take it down so we can solve question. Let's take it down so we can solve question. Let's take it down and write it down so we can solve questions from it. Oh, people are loving my videos. Thank you. Can somebody throw a Pepsi from that place? Anybody that can throw a Pepsi from there, just throw the Pepsi quickly, just from where you are. If you can do it, your exam AAE is sure. Just if I can just put Pepsi in my hand like this now, from there. All right, let's move. Are we done writing it? Are we done writing it? Okay, so I will solve one question, and why you will solve one question. Now this problem says it says a moving coil meter, a moving coil, a moving coil, a moving coil meter, a moving coil meter with an internal resistance of 100 ohms with an a moving coil meter with an internal resistance of 100 ohms has a full scale deflection, has a full scale deflection when a current of 10 milliamp flows through it. Full stop. Now says, what value of resistance would convert it to read 10 volts? What value of resistance would convert it to read 10 volts at full scale deflection? Now, this is the question. A moving coil meter with an internal resistance of 100 ohms has a full scale deflection when a coil. Now, when you hear the word a coil, we are talking about is like in this context, it's still serving as your galvanometer. The coil is still serving as your galvanometer. You understand? So you are using the coil as a galvanometer. In case they give you something like that after that time, just know your galvanometer they are talking about. So what would be the solution here? Let's write that as well. I just told you now that the coil is serve as the galvanometer. So they said the moving coil meter with an internal resistance of what? 100 ohm. The resistance of that galvanometer is 100 ohm. So we're saying RG equals to 100 ohms. Has a full scale deflection. That coil has a full scale deflection when the current of 10 milliamp flow through it. Of course, I've told you that when in this conversion of ammeter and galvanometer to voltmeter, that the current flowing through the galvanometer is the same current flowing through the what? Flowing through the multiplier. So this current that was given to us here, 10 milliamp that flows through the coil, is still the same amount of current that will flow through the what? Flow through the multipliers. So I'm saying our I, we don't need to write it as IG. I equals to what? 10 milliamp, which is equivalent to how many amp? Divided by 1000, 0.01 amp. Then after, what value of resistance? That is Rn. How do I know Rn? Because they're saying what value of resistance we convert it to read 10 volts. So you are trying to convert that coil to a voltmeter. to be able to read a volt, this volt. So Rn is what we're looking for, and our V, the total V that you want to deflect or this you want your galvanometer to be able to read as full deflection is what? 10 volts. With this now we can just slot it into our formula. And what's the formula? He said the formula is Rm equals to V all over I minus Rg. Please, it's still the same thing, oh. You know, if you simplify that one I give you, it's still the same thing. The same thing as saying, you know, if you do LCM now, you have I, you have V minus I Rg. You get it? So that is Rg. So you don't have to be scared. If you look at this one I gave you, it's still the same. Okay, somebody has gotten the answer there. Is that 900? Yes, that's the answer, 900. So maybe use of this our formula that we got. I told you that they are the same. It's still the same thing as this. Any of them works. You get it? So Rm now will equals to, let me follow the one I give you. V, which is 10 volts, minus IRG, that is I times RG. What's our I? 0.01. And what's our RG? 100 divided by what's our I? 0.01. You understand? We're following it. Then that gives us Rn to be equals to, by the time you do this, you'll be having 10 times, this times 100 gives you 1, divided by 0.01. And when you divide this, it will give you 900. So this will be 9 over 0.01, so that will be 900 ohms. If you write it like this, of course, you know that you have not completed your answer. You have to write 900 ohms connected in what? Connected in what? 900 ohms connected in series. 900 ohms connected in series. Okay. You can quickly write it down so that I can Some of you are joining in late. I already told you ahead of time that we are making use of 10 o'clock. And some of you are joining in late. So please write down. Okay, you're done, Abi. Shubhami, you're done. All right. Let's drop a question right now on the board. Who else is done? Who else is done? Okay. So I can wipe it off. So let's quickly solve this question. As I'm writing it, you can be solving it, you know, so that immediately I'm done writing it, you can just tell me the answer. You understand? Or because I know that once I'm done writing it, I'll just give you 2 minutes to get the answer. So the question says the maximum permissible current permissible current through a galvanometer G, G of internal resistance of internal resistance 10 ohms is 0.05 amp. Full stop. Then he said a resistance R a resistance R is used to convert a voltmeter with a maximum reading of 100 volts. Full stop. Find the value of R. Find the value of R and how it is connected to G. And how it is connected to G. Of course, they said the maximum permissible current through a galvanometer G of internal resistance, this is this. So this is the current flowing through the galvanometer. Of course, we know that the current flowing through the galvanometer is the same thing flowing through the watt multiplier. You get, I've told you, because they are in series. You get. So this is the resistance of the galvanometer. As you can see, galvanometer of internal resistance. This is the current flowing through it. This is the same current flowing through it. So now the resistor R is used to convert it to a voltmeter of reading this. And this must be the total volts. Okay, so now we use all these things available now to solve the question. 2 minutes. Really think this is solvable. One. Hey, that's what I'm talking about. It's so good. You just want you to take color or something. So it's good now. You do that in a class like this. What do you call it? That's how I die now. Yes, guys, for this thing, I swear. You want to say, I'm not dying. Guys, for that day, are you done? Nobody's done. Okay, somebody gave the answer. Shibomi, you are correct. 1,919 connected in series. Very perfect answer. Very perfect answer. That is very, very perfect answer. Correct. So how did she go about that answer? Very simple. She just applied what she was supposed to apply. What's our I? The I is what? 0.05. This is the current flowing through the galvanometer. Also the same thing flowing through the multiplier. Then this is our IG. Sorry, I said IG. This is our RG, which is 10 ohms. As you can see, that was the resistance. The same galvanometer of internal resistance. This. You get it. Then that's a resistor. So the resistance R is used to convert a voltmeter. So this R automatically tells that R is called Rn. Since it's converting a galvanometer to a voltmeter, you want to use it so that the galvanometer will be able to read 100 volts. That means the total volts to read is 100 volts. You get it now? So they're not asking us to find this Rn, giving these parameters that we have right here. And how can we make use of these parameters to get it? We know that our formula is what? Rn equals to what? V minus IRG, I think, over I. Yes, so making the formula now we have V, which is 100 minus IRG, where's our I? 0.05, 0.05 times RG, 10, divided by I, which is 0.05. Are we together? Then that should give us Rm equals to, when you do this, you'll be having 100 minus 0.5, 100 minus 0.5 divided by 0.05. And this gives us 99.5. We have 99.5 divided by 0.05. So if you do 99.5 divided by 0.05, I think that should give us a value of this is 99.5 divided by that should give us a value of 1990, just as you got 1990 ohms. But don't forget to add your connected in what? Series. So that's as simple as that. This thing is very, very simple. Very, very, very simple. And you see a lot in your GPEP, as you can see. These are GPEP questions I just adapted this from. You get. So we can move further now. We can move further now. We are done with converter from galvanometer to ammeter. Now we want to go to the one of the major aspects. Now we want to go to potentiometers, meter bridge, and Wheatstone bridge. And the moment we can cover those three, we will now go into Kirchhoff's law. And once we are done with that, that means we have finished everything in our electric current. That means we are good to go for electric current. We will just be solving questions, drilling questions before your physics exam. Can I write this off? Deciding a wow. Life will not end. You can take screenshots. I told you, take screenshots. O04. Yes. Then we're going to be doing O4. Like, you know, from next week now, we said our classes are going to be every day. Even the physics we do first for next week will be O4. You get it? We've been treating O4 before, but we are still going to touch it again. We did O4 with the, that was before you joined, actually. Some of you, before you joined, we have already finished O4. We have just 2 more topics or 3 more topics left from there, but we're starting it again next week. You get it? So just make yourself available for those classes. We cover the syllabus, at least it's considerably amount. You remember the plans we had? So let's do the plans to the group. Potentiometer, Wheatstone bridge, and meter bridge. Wheatstone bridge and meter bridge. A lot of bridges. Now, what's a potentiometer? A potentiometer is just a device that is used to measure the resistance of wire and the electromotive force of cells. You understand? So if you having different cells connected, are you getting me now? 2 cells connected to a particular potentiometer, which is like a meter rule with copper wire on top. You understand? You connected to it, and we'll be able to use that to measure the resistance of the wire and the electromotive force, which is EMF, which is also measured in voltage of the what? Of a cell. So let's get into it now. Let's write. Say a potentiometer, we're starting with potentiometer. A potentiometer is a device used to measure the resistance of wires and EMF, that's the electromotive force, of cells. Resistance of wires and the electromotive force of cells. Okay. Now, listen carefully. The mechanism matters a lot. Do not cramp. The mechanism matters a lot, and it's very, very easy. Very, very easy. Now, I want you to imagine we have a meter rule. Imagine we have a meter rule like this. We have a meter rule like this. And the meter rule is, of course, graduated or calibrated. And you have something like that now. Now, of course, we know this meter rule measures 100. You understand? It measures 100. Good. You now have this meter rule connected to a cell. It's connected to a cell, and this is the symbol for cell here. It's connected to a cell. I don't want you to come, just watch. It's connected to a cell. Now, from this cell that this one is connected from, you are now running another cell. You will now use that cell to measure the connection of other cells. Are you getting me? You use the connection to measure the resistance of other cells. And that means I can bring out one cell from here. And run it to one wire from there, running into a cell. You can run into a cell and connect it to a resistance. You get? Now, when you do that, this cell is going to deflect a particular length from the total length, and it might just end up deflecting this place. And we call the distance from this point deflected here to the beginning of this thing what? L1. And we can call this cell EMF1. So I said, okay, the meter. Okay, sorry, the meter. So you will now call this one L1, that's the length of the length deflected by the first cell. So I can call this one E1. Are we together? I can call it E1. Good. Now you can still have a second cell that will come out like this from this same place, from this same terminal, and run to its own cell. And we can call that one E2 to have its own resistance. And that one too can go and deflect another size of length. And we'll call it, that means from this place here, we can call that point from here to that side L2. Listen up. Now, let me do the demonstration again. Okay, so maybe you don't understand. I will re-explain. Okay, I will explain. Let's do it again. So, you have this ruler. It's just a demonstration. This aspect, you just need to understand the concept. You have a ruler now. Good. From the ends of the ruler, you connected wires up to fit into a particular cell. Are you getting me now? This cell will be generating power that will be flowing around, giving these two terminals its own magnitude. You get it? Now, you now run one cell out of it. That's why we call it E1. I think it's this cell. You run one cell E1. That cell that you are running out of one terminal will deflect a particular length out of it. That means when I say deflect, it will possess its own length. If you do it in the lab, you will see that it will actually deflect a particular length. And that length, the distance from here, where it deflects, to this beginning of the meter rod. That's what we call L1. The second cell will do its own. You connect another cell there, and it does its own, and it deflects another length L2. You get, and that will down that point, from that point where it deflects to the beginning is what we call L2. This is not the major problem. Then what you need to know from this is the relationship. And what's that relationship? E1 deflected L1, so we can say E1 all over E2 equals to L1 all over L2. This is the major thing you need to know. This is what you need to use to solve. That's what you need to solve. I get me now. Where E1 is the electromotive force of the first cell, E2 is the electromotive force of the second cell. I get me now. And then L1 is now the length deflected, or you can call it the balance point. You can call it the balance point, because this is the balance point of the first cell, and this is the balance point of the second cell. Are you getting me now? So that's it. E1 EMF of first cell, E2 EMF of second cell, L1 is the balance point of the first cell. As you can see, E1 balance point of the first cell, and L2 is the balance point of the second cell. As you can see, this second cell runs, this second cell here runs this point, and that's the distance between the balance point of the second cell. So we're going to use this expression here to solve some questions. We're going to use it to solve some questions. Will you write that thing down? I'll just write the question beside it. I'll write the question beside it. Problem. The question says the balance length of a potentiometer wire for a cell of EMF. The question says the balance length, the balance length of a potentiometer wire the balance length of a potentiometer wire, the balance length of a potentiometer wire for a cell EMF, for a cell EMF 1.63 volts, 1.63 volts is 85 centimeter. Full stop. If the cell is replaced, that means we're about to get this cell that is replaced now is going to be our what? It's going to be our E2. If the cell is replaced, by another one of EMF 1.07 volts, calculate the new balance point. Calculate the new balance point. So in that question, it's as good as they're asking you to calculate for L2. It's as good as they're asking you to calculate for L2. Are you getting me now? So in that question, now they're giving you your E1, your E2. They said the balance length of a potentiometer wire for a cell is this. That means if this is your E1, the balance point, they said, of this volt is this. The balance point was 85. That means your L1 was 85. Now, if the cell is now replaced by another one, that means if the cell now, you now remove this one and you replace it by another cell, are you getting me now? For this time, another cell is 1.07 volts. Are you getting me? That means that you need to calculate the new balance point. You need to now calculate this new balance point here. So I want you guys to attempt it and try it. Attempt the question. Attempt the question. Attempt the question. Attend the question. If you've gotten the answer, just tell me what will be the new balance point. Let's be fast, let's be fast. You don't have time. Anybody? Has anybody gotten the answer right? I've explained the concept now. The balance length of a potentiometer wire for a cell EMF 1.63 volts. That is as good as, imagine this one now was 1.63 volts. I get me, and the balance point 1.63 volts is 85 centimeter. The balance point was 85 centimeter. I get me. Then I say if the cell is replaced, that means this new side here that I demonstrated here. If the cell is replaced, that is the cell here is no more that one. Now replace it by 1.02. That is your E2. Your E1 was this, and your L1 was this. Your E2 now is now this. They're not telling you to find the new balance point. That is your L. Your L2. Or leave it. Nobody? Okay, let me solve it. That will become, based on the solution, we'll be having E1 to be equal to how many? 1.63 volts. And that E1 is 1.63 volts. Okay, Jessica, you made a slight mistake. You made 55 point something. Check your workings very well. You know, I wrote 1.63 here. If your E1 is 1.63 and your deflection for that one, that is your L1, is now 85 centimeters. Are you getting me now? And you now got your, okay, I think you got your own meters. All right. Then you now have, I thought it's centimeters, you got the meters. But even if it's meters, check your work. So you now have EMF, the second one, E2. That E2 will now be 1.0. That's going to replace the cell by a new EMF. What will now be your balance point? And we've said already potentiometer law, E1 over E2 is equal to L1 over what? L2. That implies that 1.63 divided by 1.07 is equal to 85 over L2, which we are looking for. Are we seeing that now? So I can now say, because multiplying now, we'll be having 1.63 L2 equals to 85 times 1.07. That is equal to multiply. So divide that by 1.63. So our L2 will now be equal to how many? What will L2 be equals to? So someone should do this. It's 5 times this divided by this. I think that should give us what? That should give us like 55.80. Around that figure, 55.80 centimeter. Hope you understand it. Hope you understand it. Yes, Jessica, understand. That's why I said you are still like, even if I converted, if I want to convert to meter now, I'll divide by 100, 1, 2. That will make my L1 0.85. And if I should get my answer in meters, this one now will be 0.5580. You get? So if you work in centimeter, fine. If you work in meter, fine. But that your answer in, even if you're working in a meters, it's not supposed to be 5.5, it's supposed to be 0.5580. You get, check, maybe you did not put the correct values. Maybe you didn't check the question very well. So I'm rubbing off now. I'm rubbing off now. I'm rubbing off now. I'm rubbing off now. So that we can go to, but I've done potentiometer now. I want to go to Wheatstone Bridge. I want to go to Wheatstone Bridge. I want to go to Wheatstone Bridge. Screenshot your the board so that I can wipe it off. Giving you just 2 minutes to screenshot. I want to wipe off. So immediately we're done with this lecture, everybody, you have to snap your notes and send to me on the group so that I can see what you have written so far and your solutions, because I will be giving you work to do this time. So I can wipe off. Okay, Shubhami, I don't agree. I can wipe off. So that means if you should see, they should give you a setup, like if you solve your question and they put a setup like that you are seeing that two cells are coming out like this, just remember that potentiometer and the relationship is E1 over E equals to L1 over L2. Now this Wheatstone bridge is actually easier than that, than the potentiometer. They are very simple concepts, very, very simple concepts. Now, a Wheatstone bridge is actually used to measure resistance accurately. It is used in measuring resistance accurately. You get it? And what is the Wheatstone bridge about? Let's just write it. The Wheatstone bridge. Then it is used to accurately measure resistance. Accurately measure resistance. So about your Wheatstone bridge, it's just about arrangement of resistors and the rules that guide you obtaining the values of some kind of resistors. So if I have a bridge like this, in between some resistors arranged in this format. Let me first draw the distance before I connect. Now, if you have something like this, I get you now this kind of arrangement. If you have this kind of arrangement or setup of a cell, let's call this one R1, R2, R3, R4. I get you now. Let's write it down. You have this kind of arrangement, this kind of setup. There are principles that enables you find the value of O. There is a relationship that comes in between each of these resistors that you must know. But before then, I must give you a principle. So just write down. At balance point B, if here is if I want to label now, I call this place B, I call this place our D, A and C. That's A, C, D, and D. Are we getting it now? I will explain to you now. At balance point B and D. Are you getting it now? The potential difference along this bridge is usually 0. Are you getting it now? The potential difference across this bridge is usually 0. So if you want to relate these resistors with one another, what you will say is this one all over this one. Please notice, so you are following the bridge, crossing the bridge, not this one over this one. You see this one that serves as a bridge. I get me now. This wire that serves as a bridge that protects this galvanometer right here. This is a galvanometer in between them. This resistor that crosses the bridge and this one, you say R1 all over that one, and this R1 over this one is still equals to, you go down, R3 over R4. So in this kind of questions, they will give you the diagram and tell you to obtain the value of one of the resistors. They can give you a 4, 2, 3 and not give you anything and tell you to find this one. You should know that this is the resistor bridge setup, and the potential difference across this bridge is usually 0. So the R1 over R2 must be equal to R3 over this R4 right here. Is it clear, or should I recapitulate? This is what I'm just saying. Don't go and do R1 over R3 because you do not cross a bridge like that. It is R1 over R2. Even if, as when they put the bridge like this, as when this line that I put here, they put it this way. I get it, and you say that's when you say R1 over R3. You get it? That's when you say R1 over R3. As when that line was like this. But now that like you have to cross the bridge, R1 over R2 is equal to R3 over R4. R1 over R4. You cannot do, no, you cannot do R1 over R4. You get it? You cannot do that. You cannot do that. You can only cross the bridge this format, this one this side, because you're having another node here. So R1 over R2, R3 over R4. You get it? You get it? Okay, someone asked the question. Why? Now, this is what we said. You know, I already said it before. I said something, and that thing I said was very, very, very important. I said that at balance point B, I said that at this balance point B, are you getting me now? And D, they are the same potential. This one and this one are the same potential. Therefore, the potential difference between B and D will be 0. So for a resistor R1, R2, R3, and an R4 that are connected in this manner, I get it now, in this manner, if you must obtain the relationship between them, you have to make sure, you know, this is one node here, this is one node here, these are different junctions. You get, so if you must obtain a relationship, you have to say R1 over this, meaning that you are following each segment. This one is on one segment like this one here is another segment on its own. So you can say R1 over R2 equals to R3 over R4. Please take note of that, very important. Let's see if I can bring up a question. And there's a question here. There's a question here. They said, I want to actually finish this topic today. They said, are we together now? So they drew this like this. They said, yeah, it's 4 ohms. They give us here at 4 ohms. They give us here at 2 ohms. Then they give us this side here at 3 ohms and here at R. And they call this R. And they put the line here, this place as P and this place as Q. And they put the deflection here. I get it now. Then the question says, that we should calculate the value of R. The question says we should calculate the value of R. Have you got the answer? Calculate the value of R. Somebody data has been issued that, sorry. Desire. Oh, that Desire, your data has finished and you don't have been shouting. You want 10 o'clock class, you want 10 o'clock class. They give me 10 o'clock class, you don't have data. Sorry, you. We still, bro, serious. You can't be shouting, want 10 o'clock class. Now, Baba just assume. See, normally night bundle 12, you do night bundle 250, the man has about 250 MB. You think I'm very Baba was like, no, we want to do night 10 o'clock class. And very expensive, go to use someone that I no problem. This guy is not serious. But last we finish. Okay, calculate the value of R. Now, what is the value of R? Who can tell me? Have you solved it? Who has solved it? You're waiting for me. It's you. Better solve it. Calculate the value of R. That's the first part of the question. The second part, calculate. Just do the first part test, then tell me the answer to the second one. Calculate the potential difference across PQ. Across PQ, given that the galvanometer is at null deflection. Okay, quickly, who has gotten the answer? Please, sharp. It's simple. I've given you guys the relationship. You've seen where the line is. You can tell the one that you're relating with. Quickly solve it and tell me the answer. Okay, someone has gotten it. Value of R is 2 ohms. Said value of R is 2 ohms. Okay, let's do it from that person. Is it really 2 ohms? Is it really 2 ohms? Yeah, correct yourself, correct yourself. 1.5 ohms sharp. That's it. 1.5 ohms. 1.5 ohms. Something is, oh yeah, who will tell me the answer to this one? Although I know you know how to go that 1.5 ohms. We say that your E1, that is your R1, that is this 4 here over this 2, will be equals to this 3 over the R. So cross multiply, we have 4R equals to 6. 4R equals to 6. That's, then R will be equals to 6 over 4, which gives you 3 over 2, which gives you 1.5. Who will tell me the answer to this second one? Calculate the potential difference across PQ, given that the galvanometer is at null deflection. Who can tell me the answer to that? Nobody. Quickly. Let me tell you something. The answer is 0. Some of you have started carrying virus to be solving. I've said it at the beginning already that when for a Wheatstone bridge that has a bridge like this, I said that the potential across B and D is 0. I already said it. So these questions come at your GPA so that they will do it so that you can solve. You will solve what is not solvable. You understand? You will solve what is not solvable. Good. Super me very correct 0. So please take note. The reason is because at this non-deflection that you're in the Wheatstone bridge, the deflection, the potential difference at P and Q are equal to us that the sum of the potential difference is what? 0. You get? Okay, so that's that for Wheatstone bridge. We are going to the final kind of bridge that I was talking about, which is our meter bridge. The easiest of them all, the meter bridge. Can I wipe it off, please? You guys should write fast so I can wipe it off. Write fast. I think I can wipe it off. You can screenshot. I'm giving you 30 seconds to screenshot if you want screenshot. Yeah. Okay, the last kind of bridge, Bristol Bridge. Sorry, Meter Bridge. The Meter Bridge. Okay. Now, one thing is your meter bridge is a special application. It is a special application of Wheatstone Bridge. They can ask you that is an application of Wheatstone Bridge. Is your meter bridge. Wheatstone Bridge. That means it will also measure accurately what resistor. I get me now. It will also be used in measuring resistance accurately. Thus, measures resistance accurately. Now, you'll be seeing some diagrams in your exam. I get me now. I want these diagrams are from Wheatstone Bridge. Now look at how your Wheatstone Bridge looks like. So your meter bridge looks like. You have your meter rule, of course. Right here in the word meter bridge, we have the meter rule. The meter rule is as usual calibrated. You know how your meter rule is to be calibrated. So good. From this point here of this calibration, you will have a metal that will come down like this. I get me. You have another one that will be in between, and you have one like this. This is just a diagrammatic illustration. Though. You have it like this. You get. Then from one side, you will connect the resistor, and you call that resistor R1. Then from this other side, you connect another resistor. You call that one R2. I see it now. The meter rule, you bring out metals from there like this. Then from this side to this side, from this terminal to the central side, resistor 1, resistor 1. From this terminal again to this and from this middle side to this other terminal, you have resistor 2. That is the connection. Then you can now connect them generally to a cell. You cannot connect them to a cell so that current can flow. And connect them to a cell, and this thing will be opened, of course, to allow electricity flow through it. Open, close. Okay, so what happens? What's the mechanism that we're trying to demonstrate here? The moment this happens, there will be a galvanometer here, or a deflection plate that will now deflect current. Now deflect current. Now, it is this resistance, it is this resistance R1 that is deflecting like this, So, resistance R1 is the owner of this place that we'll be calling L1. Similar to what we did the potentiometer. Why this resistance R2 is the one that we're owning this place that we're calling L2. But you agree with me that a meter rule is 100 centimeters. From here is 0, this is 100 centimeters. So it means L1 plus L2 is equal to 100 centimeters. Since L1 plus L2 is equal to 100 centimeters, I can say that my L2 is equal to 100. Okay. As you can see, they are taking the light. Hold on. I'm coming. Thank you, guys. I think you hold that.
This is for this guy.
Okay.
Wow.
Yes, yes, we are back. Let me use the white lights. So we're back. So it's actually clear. So we said L2 is going to be equals to 100. Sorry, that was NEPA interaction. We're in Nigeria. That's a proof that I'm not doing this lecture from US. You understand? So we have L2 to be equals to 100 minus L1. Look at it. L1 comes in. You get it? So this L2 here, we're saying R2 is deflecting a current of 100 minus L1. That's the remaining portion that is left after R1 has deflected its own. I get what I'm saying now. So this is just the basic concept of your meter bridge. That's the basic concept of your meter bridge. Are you getting me now? So we will now be solving our last question under meter bridge now. So sorry, I've not given you the relationship. I've not given you the relationship. So what's the relationship between your meter bridge and between that resistance and the other one? It's just the same thing as what you did in your it's the same thing as what you did in your potentiometer when you're doing your potentiometer. That one is going to be what? That one is going to be R1 over R2 equals to what R1? R1 is deflecting what? L1. L1 over what? R2 deflecting what? L2. Of course, we said L2 is equals to 100 minus L1, so we can say R1 over R2 is equals to 100, sorry, is equals to L1 all over L2, which is 100 minus L1. So can you see that now? So that's the relationship for it. Please write it down so that we can solve question, and that will be all for this. We'll be left with Kirchhoff's rule. And the thing is, you guys can do yourself good, and in your leisure time, you can do yourself good in your leisure time, solve questions, you understand, and watch videos. You know, I posted already videos on other topics in your 003, which is magnetism, electromagnetic induction, and stuff like that. Everything in your magnetism to electromagnetic induction, anything induction, magnetic, and stuff. We've covered it on YouTube. You can go on YouTube, subscribe to Erin's Impact channel, and you'll be able to view those lectures. Now, we have a question here. We have a question here that was asked. Can I wipe off the board? Okay, quickly write, quickly write. So this question now, it says, can I wipe off now? It says, in a meter bridge experiment, in a meter bridge experiment, in a meter bridge experiment, there is a zero deflection of the galvanometer. There is a zero deflection. When there is zero deflection, it means that the it is at its balance point. Everything is at its balance point. There is zero deflection of the galvanometer when L1 is equal to 40 centimeter, as shown in the diagram below. As shown in the diagram below. So they now say calculate the value of the resistance R. Calculate the value of the resistance R. Calculate the value of the resistance R. So what's the diagram? This is the diagram. They put 10 ohms here. They connected it to something like this, which is similar to what I already gave you already. Called the R. Connected this one down. Connected this one like this to down. Okay, then this one now was one that deflected like this. And they called this place L1 and called the R, called this point Y, called this place X. So then I said we should find it. And they said in the question already that L1 is equal to 40. It was given to us in the question. Let's solve it together. If you can solve it, you can start solving it. They already said in the question that what your L1 is equal to how many? Is equal to 40 centimeter. So since our L1 is equal to 40 centimeter, are you getting me now? Since our L1 is equal to 40 centimeter, it automatically means that what? It automatically means that this place here is our 40 centimeter because they labeled it for us. So we are saying to find R, we know that this 40 centimeter, this remaining place here, which is L2, this remaining place, which is our L2, the one deflected by R, will be how many? Will be how many? Since the whole of the meter rod is 100, I mean, this place here will be 60. Since L1 is what? 40. To balance 100. So let's now solve and get R. So we're saying 10 all over R. From that formula that I gave you, let me write the formula out when I wrote R1 over R2 equals to L1 over L2. So that's 10 all over R equals to 40 all over what? 60. So obtaining the value of this R, we say 40R equals to 600 because multiply. Dividing both sides by 40, you'll be having R to be equals to what? 60 divided by 40 gives us what? 15. That gives us the value of 15 volts. It means that the value of this resistance here that was able to deflect 60 is what? 15. I believe it is clear. So somebody already got the answer there. Jessica, sharp. Nice one. I can cite you from this place. That's good. Kudos. So finally, the last question I'll give you, your own question under this aspect. Okay, she want me to okay. So let me give you one more question to solve on this one, and we call it a day. Let me first of all give you one question on this one, then we'll call it a day. Can I wipe it off? Can I wipe it off? Can I wipe it off? Okay, we are talking about, is it Kirchhoff, abi Kirchhoff's formula? What, look at what he's writing. It's called Kirchhoff, not that. You understand? That's called Kirchhoff's. It's not even a formula. Kirchhoff's rule. Get, where we have node rules and this thing. So we will talk about that in our next class because of time. Our time is fast spent. I didn't tell anybody that we're going to spend more than 2 hours. Get, so and if I start saying let us continue the class, some people that in their mind they'll start be like, this man said, is it not 2 hours he said? Is it not this one he said? So let's do it like this. Or do you want to go on? Do you want to go on? Me, I don't want to go on. It's from next week that we will be going on. I want to go off. Okay, so I now want us to solve this last problem. I tick all the questions I could see from the question stuff and read them out so that I don't start acting during class. So they said in this last problem, this desire, I'm sure that, are you sure you don't need to tap small weed from your backyard? Because sometimes you used to just talk like somebody used to tap weed. I just, yeah, in class, you're talking about people following you. Why? Why should they be following you now? It's true that the guy is doing like he's tapping small weed from his backyard. In a meter bridge experiment, two resistors in a meter bridge experiment. So this is your ticket to go, your ticket to be free. You get it? You solve the question. In a meter bridge experiment, in a meter bridge experiment, two resistors, 2 ohms, two resistors, 2 ohms and 3 ohms. Oh, this guy, you don't understand. You say when others answer, you copy and paste. Let me tell you how it happens. Let me tell you how it happens. This is it. The first person that answers the question is free to go. You get, the first person that submits this question is free to go and sleep, or except they don't want to go and sleep, they want to still stay to solve. Then I will give another question. That's how we'll be giving questions till we get to the last person that cannot answer any question. That person will continue to be here, we'll be solving questions. So 2 ohms and 3 ohms occupy the left and right gaps respectively. Occupy the left and right gaps respectively. Find the balance points from the left side of the bridge. Find the balance point. Find the balance point from the left side of the bridge. Chicken now yourself. Once you've gotten the question, then you are free to sleep. Only human you make receive believe and receive or until you more. If you 40 centimeters. Somebody's got 40 centimeters. Let me see. Let me see. 40 centimeters. Yes. Jessica and Desire, you got 40 centimeters. You are correct. You are correct. You are correct. Thank you for your life. Let's solve it together. Let me solve it now. That question, people might be looking, being like, might be like, where is the L1? Oh, where is the L2? Desire, get lost. Please go and sleep. You are done. Where's L1? Where's L2? All this kind of stuff. They didn't give me L. Now it's actually very simple. Look at what you are just supposed to do. Don't worry. Once I solve this one, everybody are going to go and sleep. Okay, you got it, Chubomi. Chubomi, do you get it? I'll just joking. After this one, we're all going to go and sleep. Don't worry. So look at it. In a meter pit experiment, it's as good as they are telling you that two resistors, 2 and 3, occupy the left and right side respectively. So this is the left side. That's where the 2 ohms is. Are you getting me now? You now have to arrange it now. Then at the right side, that's where the 3 ohms is. That's where the 3 ohms is. So this will now deflect, and we don't know how it is going to deflect. But we know that since this one is 2 ohms, this one is going to be smaller, so we can deflect it like this. We know that the display will be smaller, so here it has to be wider because it's larger. So we call this place L1. So what we're looking for is L1. I get it now. We know that this place is 100 minus L1. You see that now? 100 minus L1. You get it now? So that gives us what? That gives us 2/3 as usual, 2/3 ohms equals to L1 all over 100 minus L1. And we're looking for L1. So let's cross multiply. This will be 3L1 equals to 200 times 2 times 100, 200 minus 2 times L1 minus 2L1. And that gives us, when you carry it here, 5L1 equals to 200. So divide both sides by 5. So you're having L1 to be equals to 40 centimeters. You see that now? So that's actually how to solve the question. That's actually how to solve the question. So good. Please, now I want to just use a few times to talk to you guys. Now, just listen good. I'm going to advise people because your exam is commencing and this is not shit, it is real. Your exam is commencing on the 7th and school is resuming next week, Monday. Now, I will advise you all, make sure, because from next week I told you that we're going to be doing 4 hours online classes. But at the same time, I don't know, some of you have already been able to send you messages about the practical classes that is going on. That one is the live practical class. And even the place you guys are doing your lecture is close to this center. Is a 1 minute walk, 2 minute walk. You are doing it as College of Education. Yeah. So I advise you guys, those of you that actually know, because definitely Unilag, I don't want to start saying things out here on public stuff. You might have not been experienced to how to carry out practical questions, solve practical questions. So this medium has been made available for you guys to solve practical questions. So once you know that you're interested, just DM me. You have my contact. DM me, and I will just tell you how it goes. You understand? That's it, because many students are going to fail because of practical. Many students that have read are going to fail because of practical. You understand? So let it not look like you read, you now got to the practical hall, everything is looking so strange. You get 3 months of you guys not doing your practicals in Unilag is a big deal. Don't talk of the ones you've done that you have not been giving your corrections to, you've not been taught how to do it right. Let me tell you something. Hit this exam right where it's going to really bring out the success you desire. Pay the price and just pay the sacrifice. You see, there's nothing special about the exam. It's just for you to do the right thing, know the right people, answer the right questions, and answer those questions correctly, and you get your A. It's that simple. Is it not that simple? Simple. So we will see on the group quickly. Everybody, let's just meet on WhatsApp group right now. I'll be disconnecting, so good luck to all of you. And thank you for all your loves and your likes. Thank you.